So now I want to consider still the notion of finding the volume of a solid, but instead of thinking about already having the solid and using slicing, I want to think about starting with a region, a two-dimensional region, that we can then rotate around an appropriate axis to create a solid. And then I want to find the volume of that solid. So in this video, I'm going to look at what we'll call the disk method. Essentially, this is going to be what we get whenever the region we're considering sits flush against the axis of rotation. So there's no gaps anywhere. But even within that topic, I want to consider the possibility of rotating around a horizontal axis. And then also, what if we instead rotate about a vertical axis? So to begin with, just to kind of have a general idea, consider this region that I've highlighted in green. So it's the region bounded by f of x, the x-axis, x equals a, and x equals b. One of the things that I do really want to stress in this topic is the importance of really understanding kind of the associated picture. We're going to see a lot of times that we have to focus on where our function lies in relationship to other things. And so whenever the region is being described, be very careful about which side of the function it's talking about here. Bounded by f of x and the x-axis is really telling me that we're looking under f of x. So if this is the associated picture, then we're saying revolve it around the x-axis. So imagine we're going to take this and then we're going to spin it around the x-axis, and what we're going to get out of that is a three-dimensional solid. In order to think of the volume of that solid, I can still get to our general formula by first thinking about slices. So this is back in the two-dimensional slice that we've seen when we talked about Riemann sums just for even computing area. But now what I want to think about is that if I take that thin strip, we can make it a rectangle, again, just choosing some kind of flat height here. If I were to then rotate that around the x-axis, imagine what you'd get. You would get a cylinder with height or length delta x, and then we want to think about the resulting circular face of that cylinder. Notice that we can think about the radius in relation to our function. So let's think about our process. We want to find the volume. So if we set this up, delta x, we know is going to be the length of our interval, b minus a over n, the number of slices. Then what we want to consider is that the slices we get, I was saying that they're cylinders. These are often referred to as disks, thinking about the fact that you do get this kind of circle. And like I said, because there's no gap between the region and the associated axis of rotation, then you always get these same kinds of shapes. So in this case, we're going to think about that we have that our v sub k, which I can still use that as the volume of kind of my kth piece after I spin this around the x-axis, is going to be the volume of a cylinder. So pi times the radius squared. And we already drew there that one of the dimensions is delta x, so the length of the cylinder. But notice the radius. The radius is now the same thing as the height of that rectangle I drew. If I rotate that around the x-axis, that's going to determine the radius of the cylinder that we're going to get. So that radius, we can see that if I'm evaluating to get that height there at xk, then f of xk would be the height of that rectangle, and then consequently it would also play the role of the radius once I rotate that around the x-axis. Now, again, in terms of whether or not I'm evaluating f at xk minus 1, the average of those, that's all dependent on what type of Riemann sum I would be using. But in this part, again, I'm focusing on our end goal of sending the number of pieces to infinity, in which case the choice I'm making within that subinterval is not important. So at this point, if I wanted to find the volume of that entire solid that I would get by rotating, we could say that it is approximately equal to the sum of the volume of our n pieces here, or our n disks. And that's going to be then taking the volume formula we have here and summing those from k equals 1 to n. Now, if I want to then send the number of those pieces to infinity, then we're going to get a definite integral. So I can use my formula here. So this is then defining a particular definite integral. And again, I want to focus on the delta x is now dx. My function, I want to lose the dependence on k, but I can see structurally I'm going to get pi times the function f of x all squared. And then again, for the bounds, we have to rely on our knowledge of the region at hand. So here they're a and b, because those are the x values that we're ranging over. So we see in this disk method, again, anytime you're rotating around an axis where there's no gaps between the region and the axis, and we're rotating around a horizontal axis, then we get this nice formula for computing the associated volume. Notice that pi is always going to be in there in these instances because we are getting this kind of circular type of shape out of this. So that's, again, calling back to the pi r squared formula that we have there. So this covers rotating around a horizontal axis. I also want to consider the same notion where instead we might want to rotate around a vertical axis. So, whoops, I lost my page here. There it is. So same kind of idea, and I've drawn a different example here of, let's look at the idea that now I'm considering the region that's bounded by g of y, so it's a function now of a variable y, the y-axis, and then the lines y equals c and y equals d. So again, that would be the green region here. Now I want to rotate this around the y-axis. So in connection with the first example, I'll point out that my region is flush against this axis of rotation. So we would still categorize this as the disk method. And in the next video, I'm going to talk about what do we do if it's not flush against the axis of rotation. So here, if I want to now think about the associated volume, it matters that I'm no longer rotating around a horizontal axis. I'll point out that we don't want to use rectangles like we did in horizontal rotation, because I'm rotating this around the y-axis. I don't get a nice shape out of that. Imagine there's this big gap and we're going to spin this around the y-axis, and that's going to give me this very strange kind of object instead of the nice disk that I would like to get. So anytime you're rotating around a particular axis, you want to think about the fact that we want to cut or slice perpendicular to the axis of rotation. So I don't want to draw it this way. Let me get rid of that. And instead, I can still think of the same kind of idea of what I did above, but now I'm going to slice perpendicular to the y-axis. And again, we can fit a rectangle on there by choosing some height. So notice that now when I rotate this kind of rectangle around the y-axis, I get the same exact type of shape that I got when we rotated horizontally. So I can use the same general formulas. Now, one big difference is that this is no longer delta x, this is delta y. So we would be able to, once again, go through our steps where we would be interested in the fact that delta y here is the length of our interval in y terms, so d minus c over the number of slices n. And then the slices have volume, so again, I'll call that v sub k, pi times our radius squared times delta y. That's coming from our volume of our cylinders. And now we can think about the radius is yet again still related to the height, or depending on how you orient this, the length of that rectangle that I've drawn. And we're going to get that from our bounding function g. So here I would square g of y sub k. From here on out, we're going to see the same kind of process. Then the volume of the resulting solid that I get after rotation would be approximately equal to the sum of the volume of the individual slices here rotated. And if I want to then get the exact volume, what I'm going to do is take a limit as we send the number of pieces to infinity, and that gives us a definite integral. Importantly, we see that that integral is dy, not dx. My integrand is then pi times g of y all squared. And again, to get the bounds of my integral, I go back up to my region and I see that y ranges over the interval from c to d. So structurally, this is very similar to the formula we boxed above. And so you'll note here that it's always good to pause and think about whether your axis of rotation is a horizontal or a vertical line. And if you ever are unsure whether you integrate with respect to x or y, just drop a perpendicular to your axis of rotation. So if you drop a perpendicular, like we did here, we see that that cuts into the y-axis, and so I integrate with respect to y. And the case before, over this, if I drop a perpendicular, I see that I cut into the x-axis, so we integrate with respect to x. So that's going to be the key thing to keep in mind. Now, putting all of this together, let's look at an example. If I can find it, here we go. So here, in this example, we're given a particular region. And again, another thing I really want to stress with these rotation volume problems is if at all possible, try to draw the region, because that can really help minimize some confusion. So we have the function y equals 1 minus x squared. So if you were to draw 1 minus x squared, right, that's going to be an upside down parabola that we would start pass through the point 0, 1. But one key thing I want to pick up on here is it says only in the first quadrant. So I might, if I overlook that, I might mistakenly kind of double the region I want. So if it's only in the first quadrant, well, we're going to draw it like this. So the region that we're looking at is beneath this curve and up through the x-axis there. Because it intersects kind of very clearly with the axes, notice that unlike my general cases here, we weren't given the values of x or say the values of y where we cut this off. Sometimes we will in situations where that makes sense. So r is inside here. In the first question here, we want to find the volume of the solid obtained by rotating this region r about the x-axis. So again, rotating around a horizontal axis. If we cut a perpendicular, we'd cut into the x-axis. So one thing I want to point out is that we're going to integrate with respect to x because of that. So the way that I can use my picture is, again, to think about that this is telling me integrate with respect to x. I now want to make sure I know exactly the value of these x values, so that's going to give me my bounds on my integral. So we know that we're integrating from the leftmost x value, so that's at the origin, so that would be x equals 0. And to find this x value, keep in mind that we can take advantage of the fact that y is equal to 1 minus x squared, and we know that that is when y is equal to 0. So to find that, we're solving this equation. And if x squared is 1, then we know x can be plus or minus 1. And since we're in the first quadrant here, that's how I know that the x value would have to be 1. So that's going to be my upper limit of integration. So sometimes you have to do a little bit of work to make sure you know exactly what those integration bounds are. And what am I integrating? Well, I'm going to integrate pi times the vertical distance, so the value of my function, squared. So the function as a function of x is 1 minus x squared, and we're squaring that entire thing. And like I said, now we're integrating against dx. So this would be the correct setup from our formula we saw before. Beyond this, right, we can just carry this through. A lot of times people just pull this pi out. It's just a constant, but I don't want to forget it. And my antiderivative, well, maybe let's keep in mind. So this is going to be 1 minus 2x squared plus x to the 4th. So my antiderivative will be x minus 2 over 3 x cubed plus x to the 5th over 5. And we're evaluating this from x equals 0 to 1. So plugging that in, we get pi times 1 minus 2/3 plus 1/5. Common denominator there is 15. So if we were to write all of those as divided by 15 to get 1, we'd get 15. Then this would be minus 10 plus 3. So we get 8 pi over 15. So that is what we would get if we rotate this about the x-axis. So same question here, but let's think about instead rotating this around the y-axis. So this is the same exact region we drew before. So let me just try to put that in here. But now we're going to think about cutting this way. So one really important difference is, again, integrating with respect to y. So we're going to need to think about the appropriate y values. So again, I can see that because this bottom one is at the origin, we know that that's y equals 0. So remember, this is y equals 1 minus x squared. And this point here is when x is 0. So that means that y is 1 minus 0 squared, and we know y is 1. So it turns out that the same values that we found for x are the ones for y. Of course, that is just a coincidence. There are lots of different regions where the y values can be drastically different from the x values, so you always want to be careful. And I know, like I said, I have pi. We're going to have a radius squared. And this is integrating against y because we have a vertical axis of rotation. Now, currently, the bounding curve that I have there is expressed as a function of x. But this needs to be a function of y. So in this instance, I need to rearrange that. So we have from here, so we've got y equals 1 minus x squared, which means that x squared is equal to 1 minus y. And so if I wanted to write x as a function of y, we would get, the square root of 1 minus y, ignore that little tilde there. Now again, technically it would be plus or minus, but we see that in the first quadrant, we are only looking at positive values of x. So in this instance, the function as a function of y is square root of the quantity 1 minus y. Now here, I'm squaring that because remember, that's playing the role of the radius. So this just is equivalent to pi times the integral from 0 to 1 of 1 minus y. So now we can anti-differentiate. We get y minus y squared over 2. And we're evaluating this from y equals 0 to 1. And so we get pi times 1 minus 1/2. And so we end up with pi over 2.